So this is the picture to keep in your mind. The oscillating electric and magnetic fields at right angles to each other, with the direction of wave movement at right angles to both fields. The wavelength is the distance between peaks of the fields. Now, some experiments involving light can be analysed using the Ray Approximation. This is also called geometrical optics and assumes that light rays travel in straight lines in a single medium. If they meet a boundary with another medium, they may change direction. The rays follow Fermat's principle that the path a ray will take between any 2 points is the one that will take the least time. Now, as we'll see, because of refractive index, that is not necessarily a straight line between the 2 points. The Ray approximation is only valid when the wavelength of the light is much smaller than the structures that the light is interacting with. So, for example, light passing through a large opening like a window will have rays that follow straight lines, but if the opening was really small, like a slit or a pinhole, the light would actually diffract, which means bending around the edges of the aperture. It would be the same kind of thing that you see in the picture of an ocean wave at the bottom right, where the size of the gap is in the same order of magnitude as the wavelength of the water waves, so the waves are diffracting around the edges of the gap and spreading out from it as if it was a point source. Later we'll look at diffraction that deals with exactly this, but for now we keep to rays that are straight lines. Then, as you can see, the wave fronts, which are lines joining all the points on a wave that left the source at a particular instant, will always be at right angles to the rays. Huygens' principle is a geometric construction that used wavefronts. It's a way of starting from one wavefront and using geometry to construct where the next wavefront will be. Huygens relied on the idea that a wavefront, that is, a line or a surface, is made up of lots of little dots very close together. Each little dot acts like a point source for the next little bit of wave, called a wavelet. You can see from this simulation that this is what waves actually do. Coming from the left, we have wavefronts that are straight lines. But if we have a screen there that blocks off every part of the wavefront except for just one point, then that point will act like a point source and the wavelet will come out in a circular pattern. This is the cause of diffraction. Now, if we have all of a plane wave travelling along with the wavefront being a straight line, then we can see on the line joining A and A dash that we're treating that line as a row of dots that are going to be points on the wavefront that will act like point sources. Now you can see that each dot on that line on the left emits a little wavelet. And since we're in a uniform medium, all those little wavelets are travelling at the same speed. And so the new wavefront is the line crossing the front of all the wavelets, because the sideways parts of all the wavelets cancel out and only the forward travelling parts add up to get a new line that is the new wavefront. The same idea works with a spherical wave that we've shown here as a flat circle. Now the circle again has a few dots on it that we're taking as the token points on the wavefront, each one acting as a point source. You can see that now a line joining the fronts of the wavelets will be a bigger circle that is the new wavefront.